There we are. That's what I wanted. All right. So for those of you who are here, welcome, welcome, welcome. It is very good to see you all. Happy Monday. I'm very thrilled that you all could join us today. I do have a little bit of housekeeping for the team. So all recordings and slides have been made available. If you're unable to access them, just shoot me an email so I can make sure that the links are working, but they should all be up right now. We should be caught up. If there's any issues with transcription, if there's any issues, just they're playing really wonky and you don't know what to do, please let me know and I will be happy to look into that and fix it for you. The next thing is today is Donny Pearson's favorite qubit on photons. This is, of course, the list of the remaining speakers that we have for the, we're halfway through, guys. Can you believe it? We are halfway through. So we have a couple of more things to look forward to. We have Donny Pearson here today. We have Andre, Sarah, Sophia, Abe Asfal, who I totally adore and have met before. It was going to be an amazing speaker. We also have some more bonus sessions coming up, as well as there was something specific I was going to say here. We have some bonus sessions. We have a panel coming and a lot of cool things just coming down the pipeline. So do remember that you are to attend at least 8 courses and make sure you're filling out your qubit comparison sheet so that you can keep up and learn all you can about qubits. And remember, there is a 1-page summary due. And this, of course, is only for students enrolled in the class. For those of you who are just guests here, please don't worry about that. Just sit and enjoy. So I just wanted to let you guys know that there is a bonus session today at 2 p.m., the Quiz Kit Crash Course. So a little bit about quantum computing. So if you want to do some real-time quantum computing, please join this session. You do not have to be a veteran programmer. People who are just beginning are welcome to join. Everything is in our link tree. So if you're going to attend this session, we ask that you do download your Jupyter, you download the Quiz Kit, and you can get all of that information in the link tree. So if you scan that QR with your code or with your phone, or you type that link into your browser, it should take you and you should get all of the install as well as the recordings, everything. Again, everything is in our link tree, easy for you to find, one place, one-stop shop. So please, I'm gonna leave the screen up for just a couple of more moments before I move on. And students, I will post this in our announcements so that you all can see it and have an opportunity to join if you are free from 2 p.m. to 4 p.m. this afternoon. So I hope you are all able to join. Again, same link, recordings, other resources, slide decks, future Zoom links, anything that's going to come down the pipeline can be found in our link tree. So if you're going, oh my goodness, where do I find all of this information that they keep posting? Use one-stop shop. Link tree right there. So that concludes my announcements. I'm very excited to introduce Donny Pearson. He's going to tell you all about himself. This is our 5th lecture. Thank you all again for joining us. And I am going to turn it over to Donny.
Sure. Let me share my screen. Can everybody hear me? Are we all good on that? Great. Well, hello, everyone. I'm Donny. I'm a graduate student at the University of Illinois at Urbana-Champaign. And today I'm going to talk to you about photons. And I'm the one that actually made this slide, this animation. I got the name from my advisor. But we wanted to do a little Dr. Seuss here with the 1 photon, 2 photon, red photon, blue photon for you. And today that's going to be the main topic of my talk, is on photons and how do we use photons as qubits and why are photons important. So the story I want to tell you today starts with just kind of a little review of quantum mechanics, qubits, explaining what photons are and what light is, and really what photons aren't at the same time. How do we use photons as qubits, why they're important, and then a little bit of professional development, because I know this is aimed towards freshmen and interested in getting in the field, and just kind of showing my personal trajectory for how I got here and how I got to grad school and what I do. So the first section I want to talk about is putting the quantum in quantum mechanics, just a little review. So quantum mechanics, no, it's not what the Avengers really used to figure out time travel or what Rick and Morty used to power their car. It's the physics of the very small. It is, and often the very cold. And cold is a relative term. And continuous things are discrete. And we have matter, and that is quantized by atoms, where quanta just means the smallest fundamental unit of something. But what about things like light? And light, the quanta of light, are photons. And that's the main topic of today's talk. And quantum mechanics really gives us some really interesting perspectives, and it has a lot of really cool concepts and really unintuitive concepts. You have things like wave functions, measurement, and the implications of measurement, superpositions, and perhaps the most unintuitive of the bunch is entanglement. So qubits. Classical bits, we have 0 and 1, but quantum bits or qubits, you can think of it as your quantum state, psi, is a point on a sphere, and your 0 and 1 are the north and south pole. And for measurement, you just pick some axis and you collapse your wave function, your quantum state, to a point on the sphere. And we can just describe a qubit by itself as just one sphere. So what about n qubits? Are n qubits described by n number of spheres? Well, thanks to entanglement, no, we get something really exciting. We get a joint state that scales as 2 to the n. So we get this exponential speed up. We get this exponential growth in the number of available states. And this is why quantum computing wins versus classical computing. It's in the scaling. So not even a classical computer could never simulate even a moderately sized quantum computer. And it's really just because of this scaling that gives us this exponential speed up. But building a quantum computer is very hard. You have the quantum no cloning theorem, so you can't actually copy a quantum state. That actually implies measurement. I need to measure my state in order to copy it. And qubits are fragile. There are a lot of things that can happen that cause you to lose track of your qubit or lose track of your quantum state. And so I'm just going to list kind of 2 general requirements that I kind of like to think of when I think of what makes a qubit good, or so it's subjective. So you need control and you need isolation. Control, because I need to do something, I need to interact with my qubits if I'm going to entangle them. And I need isolation. Qubits are very fragile and it's very easy to lose your qubit. And this is kind of a double-edged sword, because if I were to have a lot of control, that means that I don't really have great isolation. And if I have too much isolation, that means that it's really hard to interact with my system and have control over it. One of my favorite examples was from a talk that I went to from a company called Cold Quanta in Colorado. The guy giving the talk tried to explain making a quantum computer like taking a bunch of coins and trying to get them spinning all at the same time. If you bump the table, you're going to knock all of your coins over. But if you make the table too isolated, it's hard for you to actually get in there and spin all of the coins and get them going. So a very non-exhaustive list of qubit candidates are things like superconducting qubits that you'll see, trapped ions, and they kind of fall along this spectrum. Is there a big green line across the screen? Is that just me, or?
No, there is.
Is that?
It's like there was some annotation, and it's okay. I mean, if worst case, we just have a green line.
There, it's gone.
Okay.
It was driving me nuts. So I like to think of qubits as kind of falling along this spectrum of those two different properties. That there's one side are the best for control, and on the other side is kind of the best for isolation. And where they all fall is kind of subjective, but I like to think of photonic qubits as falling far on the side of best isolation versus other platforms that you'll see like trapped ions and superconducting qubits, quantum dots, NMR, kind of falling more towards the side of best control. So what is a photon? Well, maybe we should take a step further back and understand first what is light, and then we can answer what is a photon. So what is light has been a question that we've been asking ourselves for a very long time, and I'm going to start in the 17th century. You had Newton and Dutch physicist Christian Huygens. Newton had an argument that light is made of particles, little small pieces of light that would bounce off of surfaces like mirrors and would hit your eye, and that's what you're seeing. And Christian Huygens believed that it was a wave, and that Newton's theory was kind of was incomplete. And really, the 19th century, between the likes of Fresnel, Young, and especially James Clerk Maxwell, described that light is electromagnetic waves. And you get this from oscillating charges emit radiation in the form of a wave. It carries energy and it has momentum. And this allowed us to describe the wave properties of light. For example, you have refraction. You can see this every day. You can take a straw and put it in a cup and you see the light bend. You have diffraction. How do waves interact when they encounter some boundary? Like you can hear sound waves get around a corner. You can do the same with light. And interference. What happens when two waves interact with each other when they come together? You can have when two waves interact, if their crests or peaks overlap, they will add together and you'll get a larger peak. Or if the peak of one wave interacts and overlaps with the valley of another, they cancel out and you get what we call a destructive interference. And you can get these really beautiful patterns with light, and we call interference patterns, where the bright spots are where I have constructive interference of these light waves, and the dark spots are where you have destructive interference. And typically when we talk about electromagnetic radiation, we talk about what we call the electromagnetic spectrum, where we talk about the color and the energy of the light. On the far end, a little unintuitive, it goes from left to right, of high to low. Usually I like to think of things on the low from to high, left to right. But on the left, we have the highest energy, which are gamma rays, X-rays, the ultraviolet. And right here in this little sliver is where we see the visible spectrum. And further to the right are the lower energy, the infrared, the radio. Yeah. And so moving into the 20th century, this is really kind of the birth of quantum physics, and light was at the heart of a lot of irreconcilable things going on at the early 20th century that we were trying to describe. For example, we had what we call the photoelectric effect, where if I shine light on a charged metal plate, it'll eject electrons. And Einstein actually very brilliantly, especially for the time, kind of came to the conclusion that light had to be arriving in packets, little discrete packets, to kick these electrons off. And describing how a hot object, the radiation emitted from a hot object like the sun or a glowing piece of iron, we had what was called the ultraviolet catastrophe, which really was, in a sense, kind of a thought experiment. Classical physics would tell us that hot objects would just radiate away all of their energy and their temperature would drop, and that classically they would drop to 0 Kelvin, which doesn't happen. And the thought experiment would be, as if this is true, then the night sky would be infinitely bright from all the stars emitting all of their radiation away. And really the grandfather of, who I consider to be the grandfather of quantum, really reconciled this by saying that the energy carried by this electromagnetic radiation that is coming from these hot objects had to be discrete. It had to come in discrete quantities or quanta. And it wasn't really until the 20s that we kind of coined the term photons, and the real full quantum theory came about in the 1960s. So what is a photon? I am going to give you a one-sentence description of it. It is the quanta of electromagnetic radiation. And just as important as saying what a photon is also explaining what it isn't and describing some of the misconceptions that we have that are pretty common. So light is not made up of a stream of particles. It's not made up of a stream of photons. Photons aren't these little blobs or particles, and I can't zoom in on something like a laser beam and look hard enough and see a little ball and say, hey, that's a photon. It's just really a convenient picture to help describe phenomena in an understandable way. And it's really just the quanta of the electromagnetic fields. And sometimes this misconception can really lead to some arguments that aren't great and that are kind of missing that, and that come from this argument that are just misleading, like which way does the photon go? That is more of a product of using this convenient picture that isn't perhaps totally accurate. So moving on to photonic qubits. So just a refresher, I said this earlier, what makes a good qubit, in my opinion? Since qubits are fragile, I need control because I need to interact with them. I need to actually do something to entangle my qubits with each other. And I need isolation, which means that I have, well, not necessarily no interaction, but I kind of help mitigate interaction just to keep my quantum state preserved. And that this is a double-edged sword, that there are trade-offs between both. And again, looking at that spectrum, where I said that qubits kind of, the photonic qubits kind of fall on a very different end of the spectrum. Similarly, really regimes for, or designs for quantum computing using photons is also extremely different from all the other types that you will hear about, like trapped ions and superconducting qubits. Like I said before, we're all the way kind of over here, while everything else that you'll hear about is kind of on this side. And since it's so different, I don't really want to talk about photonic quantum computing today so much, and I really just want to talk about the importance of photons, because the main takeaway is that photons are important, and regardless of whatever platform wins the race to build quantum computers, photons and photonics and that technology is going to be essential. So photonic qubits, why are they so isolated? Well, photons don't interact with each other. They don't have any fundamental property about them that allows them to interact. They don't have mass. They don't have electric charge. And so, sorry guys, we're not going to get lightsabers anytime soon, which I'm really sad about. I'm devastated. But light does actually interact with matter, and that gives us some amount of control. So we are actually able to interact with photons in some ways, just that photons can't interact with each other. We have to use matter kind of as an intermediate for that. And it's easy to encode. And what I mean by that is that you can do a lot of things with commercial optics to do this, and that there are a lot of perhaps not immediately obvious ways to make qubits out of photons. So here's another non-exhaustive list of different kinds of qubits that you can make using photons. Polarization, the way that the electromagnetic wave is oscillating, that direction, you can pick an orthogonal direction of that. Color, you can pick 2 different colors of light and use that as a qubit. Time, if light moves at the speed of light, if it has 2 different paths that it can take that are of different length, the time that the photon takes to arrive can be your qubit. And similarly, just 2 different directions in space can be a qubit. And doing a lot of this is actually pretty straightforward, just using commercial optics that you can buy to generate qubits. And why are photons good qubits? Well, light is fast. It moves at the speed limit of the universe. It can travel very, very far without getting lost. Light travels about 96 million miles from the sun and arrives at your eye, and it does that in about 8 minutes. And therefore, it's excellent for transmission. So I can send information very far. And light actually has quantum behavior at room temperature, which like I said earlier, that temperature is a relative term, and I'll kind of explain that. If you think of temperature as the average kinetic energy that something has, the average temperature of something like visible light is actually pretty hot compared to room temperature. The average kinetic energy is that temperature that it corresponds to is pretty close to like the surface temperature of the sun. So if quantum things are usually happen at temperatures that are pretty cold, room temperature is by comparison pretty cold. We are over here at about 300 Kelvin, and surface temperature of the sun is about 6,000 Kelvin, and light kind of falls around 5,000 Kelvin. At least visible light anyway. And so why are photons important? Who really cares about photons? Well, or light for understanding their science. And this is another non-exhaustive list. Anywhere from biologists, chemists, astronomers, the military, people doing medical diagnostics, and even our field and quantum information, people trying to build quantum computers, and even people trying to describe and test fundamental physics. People like in quantum biology need very low levels of light to probe biological samples. You can't just blast a cell with a bunch of light and not damage it. Chemists, if you take a chemistry class, pretty much any kind of spectroscopy you use, they care about light. They care about understanding light. Astronomers, LIGO, even the military, you may have heard of this LIDAR. It's a lot like radar, except it uses light for doing your kind of 3D mapping and detection. Medicine, there are some really cool quantum technology going on with medicine that uses photons. And so I'm going to give you some examples just to kind of illustrate all these different applications that you can have. So quantum information, what do I mean by that? I just mean harnessing the quantum degrees of freedom of a system for kind of generally these 3 purposes: for communication, computation, and precision measurement. And since we care a lot about quantum computers and building a quantum computer, the first example I want to give you is what we call a quantum network, where consider having what I call these nodes, which are just anything from a quantum computer to just a group of a couple qubits, and I need to connect them in some way. Well, how am I going to connect 2 very distant quantum computers that are, in the same vacuum chamber or something? Perhaps they're in a different city or in a different country. Well, the way that you're going to do that, the only way that you can actually do it is with photons in optical fiber. That's the only way you can transmit quantum information, because you have to connect quantum things in a quantum way. And these nodes, like I said, can be anywhere between a whole quantum computer or just a couple qubits. There are actually people who are thinking of building quantum computers rather than just having a quantum computer that has a lot of qubits, to just taking a bunch of really small quantum computers and connecting them together. And the whole task of these connections is just to generate entanglement across these nodes and connect them together. And the only way to do that is going to be in optical fiber with photons, because photons are great for transmission. They're quantum at room temperature, and they're very, very fast. Another one, this is kind of all the rage of the 80s and the 90s. It's what we called quantum cryptography. So classical cryptography is based on, encryption is mostly based on doing things that are hard, that are having problems that are hard for a computer to solve. And this is very imperfect security, and you can have eavesdroppers. Quantum cryptography, on the other hand, is perfect security based on fundamental physics, or the fundamental laws of physics, and it's based on measurement. And we don't necessarily mind eavesdroppers, and we can really tell if someone is trying to eavesdrop or spy on us as we try to transmit sensitive information. And this just boils down to the really cool implications of quantum mechanics, that you can't copy a quantum state and you have to make a measurement. So if I have two parties, Alice and Bob, they're trying to share some information, and I have an eavesdropper, Eve. Classically, she'd be able to eavesdrop, and let's say they're sending, Alice and Bob are sending electrical signals between each other, and Eve can just pick off a little bit of that electrical signal and maybe throw an amplifier after what she's done to kind of erase that she has really done anything. Alice and Bob can't tell that she's spying on them. Well, you can't do that quantum mechanically. There's no way to build, for say, an amplifier. I can't copy the quantum state that I'm trying to measure. So if Alice and Bob, say, are sending some information, and its probability, its wave functions, its modulus squared, looks something like this. And it's the probability of being in some state of position, energy, momentum, whatever they are measuring, looks something like this before I measure it. What Eve is doing when she picks off this information to spy on is she is collapsing the wave function. She is making a measurement. And a lot of these schemes for quantum cryptography, a lot of these protocols are done in such a way that Alice and Bob will know right away that their data is compromised because Eve has made a measurement on their data. So this is perfect security. Another field is quantum sensing, where we get an advantage in making precision measurements. I thought this was a really cool example from a talk that I went to from someone named Ron Walsworth. He was at Harvard at the time, but now he's at the University of Maryland, College Park, and they have what they call a quantum diamond microscope, which they're actually able to use defects in diamond and photons to actually make these really cool, well, they're able to do a lot of things, but the one that I found the most interesting is that they were actually able to do enhanced early cancer detection, where they're actually able to take this kind of, they have a comparison where they have this conventional optical image that they would take for screening cancer cells in a blood sample, versus what they're able to see with their quantum diamond microscope, and they're actually able to see a single tumor cell in this sample of human blood, which I just thought was really just amazing that they could do that, and really got me excited about just what this field can accomplish. And the last thing I wanted to really talk about with this was kind of fundamental physics. You've probably heard in the last few lectures about, quantum physics, quantum mechanics, and it's all really weird and very unintuitive. So how do we know that quantum theory is right? And really, this was a really big discussion, especially in the 1920s when it was being developed, and a lot of people had problems with it. They were saying that that our world, the quantum world, is deterministic. It is probabilistic, that it all relies on measurement. Like if I have a photon from an unpolarized source, what's its polarization? Well, it's undefined until I make a measurement. And a lot of people had a lot of problems with this, including Einstein, actually very famously Einstein. And he argued that there is something called local hidden variables, which just means that there is some property or variable that we don't know, that we may not ever have access to, that fully describes our quantum state, and that quantum mechanics at the time was incomplete. And that's pretty reasonable. You don't expect that I have to turn around and make a measurement of something for it to be there. It's just so unintuitive that a lot of people actually really disagree with it. I think if I was back in the 20s, I would be on Einstein's side about local hidden variables. But this is really illustrated in a very famous paper by Einstein, Podolsky, and Rosen, where they argued in favor of local hidden variables. And they had a thought experiment that is generally referred to as the EPR paradox, where I have two parties, Alice and Bob, and they share an entangled state. Alice takes one half, Bob takes the other half. And then Alice and Bob are somehow separated by a very vast distance, say light years apart. And Alice makes a measurement on her state. She instantaneously knows and determines what Bob's state is. And Einstein, Podolsky, and Rosen argue that this violates causality. This violates faster than light transfer of information. And it wasn't until kind of the 60s that somebody named John Bell came around and wrote down a very profound mathematical statement that we usually call Bell's inequality, which is a mathematical statement that either that really no local hidden variable theory can ever reproduce quantum theory. And that if Bell's inequality is violated, then quantum theory has to be right. And there's no such thing as local hidden variables, and the world is very weird. Well, this has been done, and at the heart of it was photons, and using and generating entangled pairs of photons was done to really explore this. And that's been kind of the heart of probing quantum theory since the 70s, since we've first been able to generate entangled states, which was done with photons in, I think, 1972. And this is kind of the heart, well, a large part of the field of quantum optics, which is studying the quantum nature of light. Yeah, and there is a caveat of the EPR paradox. Alice and Bob actually can't share information fast with each other faster than the speed of light. So quantum theory is correct, and none of the laws of physics are broken. They're not violating causality or anything like that. Yeah. And so last, I kind of want to end on some kind of professional development. Like, where did I get where I am? Like, at one point in time, I was a freshman in physics, and I was like, oh, quantum stuff is really cool. How did I get to where I am, where I'm actually a grad student, like a senior grad student in my lab, trying to get my PhD? So I have this nice professional photo of myself with my advisor from somebody named Brian Stouffer. I forgot to put his name and acknowledge him. So what got me into physics? I always wanted to do something in science. When I was really, really little, I really, really liked Jurassic Park and dinosaurs, and I still do. But when I was really little, I wanted to be a paleontologist. And when I was in high school, I actually had this awesome opportunity to go to Costa Rica 3 times to study biology. We studied leafcutter ants and black sea turtles. Coolest thing I've ever done was giving a sea turtle an ultrasound. And when I did that, and I did research in college, and I majored in both chemistry and physics. was very difficult, but I had a very hard time choosing between the two of them. And I ended up working in the subfield of physics, atomic, molecular, and optical physics, which allows me to kind of do some of both. I was always really interested in the more atoms part of chemistry and physics, so this kind of allows me to do a bit of both. So what is kind of the daily life of someone in this field, especially in grad school? Personally, I get to play with lasers all the time, which is pretty cool. You tell people that you get to play with lasers and you show them pretty pictures of lasers and they're like, oh, that's so cool. Often my experiments are really cold. I work with cryogenics. I get down to liquid helium temperatures. So on our scale, that is about minus 456 Fahrenheit, and absolute zero is minus 459 Fahrenheit. In experimental physics, at least in my field, and in my lab, you work a lot with your hands. You're building your setups. You build and repair electronics. Sometimes you got to do your own plumbing, like with cryogenics. I do actually a fair bit. I sometimes do a fair bit of coding, anything from plotting up data to theory projects. And sometimes you do things like this. You do some writing and you do presentations and you do outreach and you can talk to people like you and try to get people interested in your field. But not just in grad school, but in college, naps are key, coffee is essential, and so is drinking water. And so what is my PhD thesis in 60 seconds? So I said that any kinds of quantum computers or quantum systems, they need to be connected in some way, and it's going to be connected with photons and optical fiber. But what if you actually need to hold on to that information and that is stored in the photons? Well, you need to use matter to actually hold on to it. And what I'm doing in my PhD is what we call a quantum memory, is designing what we call a quantum memory. It's a device that can store single photons. So over here, I have this squiggly line representing a photon and these little dots being the atoms or the matter. Photon comes in, gets stored in the matter for some amount of time, and then at some later time, we retrieve it. And what I personally do is I characterize new materials for making quantum memory devices. And I do this with a family of atoms called the rare earths. And we do this at cryogenic temperatures. And our atoms are in solids. Right here, I have one of our materials with the rare earth atom europium. I am doing an experiment called fluorescence, where you send in a very bright, very high energy beam, and then you look at the photons that are emitted from it that are lower energy. So I'm sending in violet light, and I am retrieving yellow, orange, red photons from this. So what do I want to be when I grow up? I'm in grad school, so that's a kind of temporary thing. I'm still in school. Well, my plans of being Spider-Man or Batman haven't really shaped out so far. But anything from industry, I could join a job and be an engineer or work in a national lab or the private sector. Lots of people in our field go into finance. There's also academia. I'm not totally sure, and it's okay to not know what you want to be when you grow up. I know at 18, 19, when I was a freshman, I certainly didn't know, and at 27, I still struggle with answering that question. And the last thing I want to end on is just some general advice I wish I had when I was a freshman. I always really liked this quote from Niels Bohr, but there's no such thing as a dumb question, in that you should be able to ask questions and not be afraid to ask questions. Admit that you're wrong, or admit that you don't know something. There's so much knowledge out there that it's pretty ridiculous to expect somebody to know everything, and that you shouldn't be ashamed of asking a question. And it's okay to fail. It's okay to make mistakes. That's all a part of personal growth. You can make a terrible mistake. You just have to learn to forgive yourself and move on and learn from it. That is more general life advice than being a physicist. But often a physicist is a person who learns from their own painful experience about mistakes. That is a lot of science, is making mistakes and learning from them. Something I wish I knew in college is that your time is fleeting, so make the most of it. There are a lot of things I wish I did when I was in undergrad. 4 years may seem like a really long time, but it's really not. Especially when you're a freshman, it seems pretty daunting, but when you're a senior, you're like, where did that time go? And perhaps the most important thing that I learned in college was from a late professor of mine. Is, may sound weird, it's to learn how to learn. That makes any sense? Is that really, it's really important to invest in understanding how you personally understand and intake information, and how you learn, and really mastering that. And that when you kind of master how you learn information, it becomes much easier to tackle understanding things that you couldn't that you didn't think you could understand before. Great. So I just want to thank my group, my advisor Elizabeth, my postdocs for the other grad students in my lab, Sean Long, Tatum, Danielle, Ashwith in our undergrad, Anakith. And lastly, I just want to thank all of you for sitting here and listening to me for the last, hopefully 45 minutes, and talk about photons and say the word quantum way too many times. Great.
Thank you, thank you, thank you so much, future Dr. Pearson. Are there any questions for Donny?
I have a question.
Mm-hmm.
So my question is kind of two-part question. First is, what are the advantages of photon-based quantum computers? And the second part is, where do you see photon-based quantum computers on the race of reaching quantum computing? Like you have ion atoms, superconducting. So where is photon-based quantum computer exactly?
So photon-based is very different. But it is very interesting. What makes it very easy is it's just kind of easy to encode and entangle. But it has problems in scaling. When it was first kind of come up with, like designs to actually make a sufficiently large system were really, really big. It's like, oh, well, my quantum computer would have to fit in 3 gymnasiums. Like when they were kind of thinking of this in the 90s. And the whole point of it was that I want to try to make this compact. And I don't really know much of the status of it now. It's gotten they've kind of gone on different routes. But I would say that it's still in the running, but probably the 2 most popular platforms right now, and that the most money are going into, are trapped ions and superconducting qubits. I hope that answers your question. Right?
Thank you, Episode. We're going to go to Achintia. Could you go ahead and ask your question?
Yeah, sure. First of all, great presentation, Donny. Good
you.
job. Yes, I really enjoyed it. So my question is about storage of these quantum states of in a photon. So let's say you create a superposition state on a qubit, which is a photon based on frequency or whatever. I can understand that it can be used for gate computation. So you give some 2 input and you get an output. But how do you store this? Because to store a quantum state in photonic computing, you would also need to store the photon, which is not possible, right?
That you can absolutely store the photon. That is part of something you can pull up from light matter interactions, is that you can actually store the information, the coherence, the phase information of a photon in matter. And you can essentially what a quantum memory is doing, like what we're doing to try to store it, is you map the state into the atoms, and then the atoms will then, like through absorption or something like that, and then it will eventually emit a photon that has the same phase information, and essentially just holds on to this, it carries the same information of the photon that was originally stored. Does that make sense?
Yes, basically it's the James Cummings Hamiltonian.
Exactly.
Yeah, for the like matter interaction. So
Exactly.
what would be the possible candidates for on the matter side for storing such states?
So lots of people have studied alkali atoms in vapor. That's probably the most popular platform for this and has been used for this for a while. For us, we
I'm
are
sorry,
doing
well, which atoms? I misheard you.
the alkalis, like rubidium, cesium.
Okay, got it. Thanks.
Just they have a very simple level structure that you can write out. Like you can write out the Hamiltonian, you can write out the states. For us, we are working with a weird family of atoms called the rare earths or the lanthanides to try to do this. They have a very unique electronic structure that allows you to store photons for very long periods of time.
Like Redbook states.
Yeah, exactly.
Okay. Thanks, Donny.
Yeah, you're welcome.
Vincent, we'll go ahead and go to your question.
Hey, Donny. So some articles I've been reading lately mention Rydberg polaritons. And what's the relationship between a Rydberg polariton in regards to quantum computing and a photon? Like, where is it on your continuum there?
You know, I don't actually know. I'm still pretty new to Rydberg stuff myself. I don't actually have an answer for that.
Okay.
Are there any more questions from the group? Well, if not, thank you all. Oh,
Maybe I can ask another question.
sure.
Yeah, so Donny, then can you also speak about the scalability of these photonic quantum computing? Like, for example, there's this already a startup, right? I think it's something called as Psi Quantum or something, which uses photonic chips, basically photonic crystals, to develop quantum gates. So how big can you make it? Like, can you go to like 1,000 qubits? If yes, then why aren't we doing it? And if no, what is stopping?
So I don't know actually how many qubits you have, but a lot of it has to do with this on chip. Some of the major problems are actually being able to couple the light in and out of these chips. That is a huge part of the problem with them. Well, a huge part of the mini problems with them. So you have really, really low efficiencies of actually being able to send the light in and actually retrieve it. I know a couple people that are working on it. And that's kind of one of the kind of limiting factors right now that I know of, that they're really trying to get around. And some of it has to do with actually machining things and actually kind of etching like these really small structures.
So basically this is because light usually does not interact with matter. So it's because of weak interactions, is it?
Yeah, it's weak and it's hard to couple light into very, very small structures. Just like mechanically trying to point like the tip of an optical fiber and get it really, really close, and do this in such a way like inside of a cryostat and things like that.
Okay, thanks, Donny.
Yep.
Are there any other questions?
Well, I've got a quick question.
Go ahead, Zach. Yes.
Donny, could you speak to the challenges of working in a solid when trying to do quantum stuff? How that's, how that you're trying to keep things isolated and stuff, but in a solid, your atoms are touching other atoms.
Yep. So for us, we actually have to get to cryogenic temperatures. If you think of a solid as just kind of a lattice of atoms, they're all shaking and moving inside. But when you cool them down, it gets not as noisy. That is kind of our main concern, is just that a solid is really, really noisy. The only way I can really get over that is if I get really, really cold. So our solids that we have to do our experiments in are at 4 Kelvin. So they're at minus 450 Fahrenheit. Or, well, I guess that's 452, but or even colder, like we get to like 1.7 Kelvin or 1.4 Kelvin. So we have to get really, really cold to see this behavior.
I see. Liquid helium type temperatures.
Exactly. I work with
Okay.
liquid helium. I just ordered a doer of liquid helium this morning for my
I
experiment.
see. Cool. Thank you.
Yep.
I don't think I see any other hands raised. All right, well, thank you all for joining us. We thank you for coming today. We will post this video and a PDF of the slides shortly. And thank you all again and enjoy your week. Good luck on midterms for those of you UCLA students.
Thank you for having me.
Thank you for joining us, Donny. Thank you so, so much. It was amazing.